Good morning, everybody. We would like to get started. And let me also say jó szerencsét. That's our traditional miners meeting, which means here in Sopron. It was jó szerencsét, which means good luck. That's traditional miners meeting. And I'm mentioning this to you first to give you like a first impression of our background and culture here. But also, I'm mentioning this to you because some people, as you walk around in the botanical gardens here, may, as you come opposite to you, they may say your serenity, so you don't be surprised. And just kind of try to imitate the opening or something like that, so you can do that if you want to. And I would like to welcome you very warmly to the third workshop of the Motivation Erasmus K2 project here in Sopron, Hungary. And I am very nervous, very excited, and very happy to have you guys here. And I hope that you will have a great time here in Sopron. And without further ado, I would like to introduce to you Dr. Tibor Alpár, who is the Dean of our faculty, the nyugat-magyarországi faculty, formerly known as the Faculty of Food Sciences here in Sopron. And I asked him to give you tell you about 50 minutes about our university and most of all the nyugat-magyarországi faculty.
Thank you very much, also, let me say a warm welcome here in Sopron at our university. It is a very good chance to make more cooperations, to get to each other, to find new friends, to find maybe loves, and to widen your knowledge. Our university, University of West Hungary, is a quite old university here in Central Europe. It was founded by Empress Maria Theresa in the 18th century. And it has a long history, a long tradition, special traditions, as also mentioned. Also, greeting is special, and we have special traditions called Shelmet traditions, which was considered by the UNESCO in the last year as a part of the World Heritage, cultural heritage, these traditions of our university. And it was started in Chemnitz, recently called Gdańsk. And after the First World War, the academy got moved to Sopron, and town of Sopron gave this nice place to establish the university, to conclude the studies here in Sopron. Recently, our university is settled in several towns. It is a network university. We have 8 faculties. One faculty is in nyugat-magyarországi. It is for agriculture. There is a faculty for pedagogy in Győr. And there are 2 faculties in Szombathely, one for pedagogy and one for natural sciences. And 4 faculties are here in Sopron. This is the center of the university in Sopron. We have here forestry, faculty for pedagogy for small children, for kindergarten children. And there is a faculty for economics, and there is our faculty, which means our faculty for engineering, food sciences, and applied arts. The university has about 8,000 students in this town, and itself our faculty has 800 students. 800 students for several courses. We have BSc, MSc level courses, and also PhD courses for academic research. Our main courses, of course, courses for good sciences or simple engineering, the BSc and MSc level. We also have industrial design engineering. We have information sciences. We have mechatronics. This one in BSc level. All the others are in our we have several acts, architecture, design, and graphic design. So you might ask, how can these different forces come together? It's very simple. Everything is based on wood processing. So when you consider wood processing, when you visit a wood processing company, you can imagine that mobile techniques, automatization requires marathons. And there is no companies working without information sciences, without computing. So it is very important for us, the IT section. Also, if you want to sell your products, you need one industrial design on both sides. Industrial design as an engineering subject, and also design as an applied art. Of course, pure design is for how anything looks like, but maybe it doesn't can work, doesn't can operate. It's just a good looking thing. That's why you need some engineering beside the design to make it operate and to make it cost effective. And also, one of the main tasks of wood industry or timber industry is architecture. You come from example, from Finland, you can notice that wood-based buildings are very important, and this is a very important end of use of stone timber. Also, when we are talking about graphics, it can be also important when we are talking about packaging. We consider also by wood processing the paper industry as a side product. It is also made either from wood, or can be made from wood. And as you see, your small booklets, these are also graphically designed. It's a typical Hungarian design, it's a traditional design. So a graphical design is also important to sell our products. This means that at a faculty we have several courses, several competencies, and the students can know each other. We have shared projects where different students can take a part, and they can work together, so their knowledge will be more widespread. They will know each other's work, each other's possibilities. So our engineers and artists will be probably more competitive on the market than other institutes similar students at the initial courses. This building is a quite new building. It was started operating in 2012. This is called Natural Resources Research Center, which introduces us that at this campus, in this area, we have two faculties, the faculty of forestry and faculty of engineering, wood science, and all of that. And we are thinking a little bit green. So we are working in nature. We are working with natural products of nature. And this is a research institute to make the researches in this field. We have here in this building about 7 laboratories, different laboratories, and a workshop for education. And these laboratories cover from genetics of plants to wood-based composites, to surface interaction, chemistry of food, soil chemistry, soil composition, wood anatomy, and all interesting things about wooden surroundings and environment. Also, we have laboratories for paper research, for metallics, There are three aims of these laboratories. The first, of course, education. It's very important because this is our first step. But besides, we have to do research. The second is research and innovation for companies and for European projects also. And the third is accredited services, accredited testing services for industrial partners to check their products, to make available a continuous high quality production. I hope you will enjoy your time. If you have any questions about our university, you may ask our students here. People they will value here. And please visit as much places here as possible. Enjoy your time. Good luck.
Thank you very much, Igor. And I was thinking that we could make a little brief introduction to one another. This is the next point in the program. Since we already have the next presenter here, maybe we can wait until the end of the next presentation, which will be about a little cultural information about Hungary, about Stockholm, and also about Hungarian culture, as we have done in the past in Finland and Slovakia and the same thing in Hungary. And for that, I would like to welcome Károly Horváth here, who is the head of our PR center here at the university, and he will be giving this presentation.
So, welcome to Hungary. My name is Károly Horváth. I'm working here at the university since this March. I've never been in the university as a teacher before. This is my first presentation at the university. Let me tell you something about Hungary. First of all, just an Italian scientist who won Nobel Prize in 1938. He said that the extraterrestrials are already among us, and they are called Hungarians. So we are. Okay, so who we are, where we live, several key facts about Hungary. As you see, our beautiful small country is around 93,000 kilometer square kilometer. Our population a little bit less than 10 million, and our capital city is Budapest. Our official language is Hungarian. Parliamentary republic, and we have Hungarian forint as a currency, which is around 310 forints, is about €1. So, to know something about our language and why we are not speaking languages, and I'm also not speak very well, I know. So these are, let's say, the languages of Indo-European languages. You can find Hindi, Bengali, Spanish, Italian, English, and while there are some Finnish here, so let's see that we came from a completely different roots, which has two sides, the Hungarian and the Finnish. So that means that we are somehow relatives, but unfortunately we doesn't understand each other. Basically, the grammatics more or less similar, but even we don't have too much word which is common. So, some really short presentation about our history. So, in 896, 7 tribes came to this territory. Then, in 1003, founded our kingdom. Then a little dark ages came, And then let's say, which is already well known, the Austro-Hungarian Empire take place from 1867. And unfortunately, in 1920, the Treaty of Trianon, we lost 2/3 of our country. From 1989, there was a transition from, let's say, from the socialist area to the, let's say, our democracy. And since 2004, we are the member of the European Union. So, as I told you, our capital city is Budapest. Some pictures about the capital city, just to have a kind of impression. That's quite interesting. That was built from the millennium, and in the middle you can find the 7 tribes who came to this territory. And in the middle, Arpad, who was the leader of the 7 tribes. And then you have to know that wherever you dig a hole which is deep enough, thermal water will come up. So we have many thermal water below the dirt, let's say. That was built by Eiffel. And the city with the Danube, and just a few pictures. That's our National Theatre. And of course, you can see so many pictures about Budapest because I'm living there. Quite close to my heart. And then again back to Hungary, just few cities which you have to know. And this Miskolc is quite close to the Slovakian border, and probably you know Tokaj, which is well known about the wine. Also one of our heritage, Orlókor, which is really a beautiful small city. This is Szeged, picture about Debrecen, Pécs, and of course the Lake Balaton, which is the warmest lake in Europe. And I think this place is really amazing. I told you, really amazing. So let's talk about Sopron. My colleague just arrived. He will tell you a little bit more about Sopron later. I will finish my presentation and then I will pass you the possibility. This place is very well located because Pozsony is quite close. Also, Vienna is quite close, so it's a nice triangle here. So, actually the city, some pictures, and you will find nice places here during your stay, I'm sure. And our university. And while you know already something about Hungary, I prepared a funny quiz just to check your knowledge. Probably you know her. Is she Hungarian or not? No. Okay. So, yes, her mother was Hungarian. Okay, second, Goldie Hawn. Is she Hungarian or not? No. Okay. Ron, she's Hungarian. Okay. Adrian Brody. Is he Hungarian or not? Yes? Okay. Yes, he has Hungarian blood, and also Houdini, interestingly, he was also Hungarian. Anyway, First good answer, a chocolate. Good kids. Let's continue. Okay, Tommy Curtis. Yes, he's Hungarian and he was also speaking Hungarian. Good answer. Okay, Peter Falk. Yes. He's Hungarian. Even his family was as known that there is a city, there is a street called Fort Mixel in Budapest. Rachel Weiss.
Yes.
Yes. Who said yes? Okay. She had a Hungarian mother. That's right. Okay. Below, it's not a question. He was Hungarian. He was known as Dracula in the early ages of the film. Okay, Johnny Weissmuller. In the left, not in the middle, in the left. Yes, he was also Hungarian. Probably you doesn't know that William Fox, the founder of 20th Century Fox and the News Corporation, was also Hungarian. Adolf Cukor, yes, Hungarian. We have many questions, so be sure that you will get some. Andrew G. Weiner, yes, who said that? Okay, can I drop you a chocolate? Thank you. Okay, Jamie Foxx. No. Who said no? Yes. Correctly. Because he's American. Okay. The Simpsons was also created by a Hungarian guy, Csupo Gábor. Okay, quiz number 2. Who knows this band? Okay? You already had a chocolate, so you don't have any more. So this is Red Hot Chili Peppers. Flair is Hungarian. Okay. Who knows this band? Older generation, come on. Simon and Garfunkel. Yes, Paul Simon is Hungarian. Okay, Kiss, probably you know. Again, Gene Simmons was, he is Hungarian because he's still alive. Okay, even you can see the tattoo. Yes, he's a Hungarian guy. Older generation, jazz music. Keith Jarrett, Hungarian mom and grandpa. Leslie Mandoki, also Hungarian. Surprisingly, Helen's Borisov, Hungarian mother. Doppler brothers from Dire Straits, Hungarian father. And unfortunately, he's not alive already, so he's Gábor Szabó, one of the best jazz leaders in the world, is also Hungarian. Kesha, Hungarian grandparents. Okay. I still have some. Linkin Park. He has Japanese father and Hungarian mother. Okay, after finishing this, maybe that will be also interesting. Who knows this guy? Viktor Vazarelli, Vásárhelyi Miklós. Maybe this girl? Nobody knows? Hungarian. And this one? Girls even doesn't know? And now? Probably you already heard about the Pulitzer Prize. Joseph Pulitzer was also Hungarian. Robert Capa. Interesting, it's not enough to have talent, you also have to be Hungarian. I think that's good. saying. Everybody knows that Nicholas Sarkozy is Hungarian. Charles Simonyi, father of the excellent Word at Microsoft.
Also, may I say some of the guy who affected me with that, used to work here.
Also Andy Grove, founder of Intel, also Hungarian, and surprisingly Andy Warhol is also partly Hungarian. Sorry, there was a mistake. Somebody, I don't know what I did. Anyway, you have to know that this presentation software is also Hungarian. Okay. Sorry for this. I did something wrong. Okay, some non-Hungarian, Queen Elizabeth, Barack Obama, Arnold Schwarzenegger, and others. Let me tell you something about the inventions. So probably everybody knows that Rubik Erno created the Rubik cube. Who knows something about this invention? Theo Inder created the ballpoint pen. Also, carbonated water, nyugat-magyarországi, vitamin C, Szent Györgyi Albert, safety matches by Irene József. Probably most of you have already some kind of car, and the carburetor was created by two Hungarians. Also, the electric train was created by a Hungarian guy. T model or T model was also made by two Hungarians. Not surprisingly, the Volkswagen Käfer also made by a Hungarian guy.
Well, you can see this Stockholm direct next to the Austrian border. Here is Vienna. It's about 40 minutes from Stockholm. But first of all, see some pictures from Stockholm. The sign made at last year the World Festival, the best festival in the world. We have a beautiful old city. You can find here some houses, which is older than United States of America. This is our fire tower. In the old times, the people are searching here from here the fire, and then it was the fire department and saved the whole city. That is our theater. Actually, that house was built in the 16th century, so it's really, really old. Stockholm by night, it's a beautiful town. Yeah, as you see, we have a lot of forest where you can go to trekking, chill out, and so, and we are direct next to Austrian border. You can go in the winter skiing. The first ski place is Semmering. It's about 60 minutes from Stockholm. It's a quite good place to ski. The other big mountain that is here in the near. This is called Schneeberg. You can go there to trekking and skiing too. It's a good program for a long weekend. So as I told, Vienna is about 40 minutes from Sopron. So if you have a free Saturday, then you can go and see the beautiful city. In every year, before the Christmas, there is a big Christkindlmarkt in German language, and you can buy everything that you need for your sad statement.
Loved ones.
Yes, exactly. So Vienna is also a beautiful city, almost as Sopron. And Vienna has a park, it's called Schönbrunn, that is a castle. There that was the summer residence of the Habsburg dynasty. There are many concerts, and you can see there were a lot of people in that summer too. It's a beautiful park. Yes. Then about 60 minutes from Sopron is Schwechat Airport. You can reach the whole world from here. So, and that is the Lake Verte. It's only 10 minutes from Sopron. You can go here to sail. Yes, to swim, eat some typical Hungarian fish dishes, and also language. And Skároly told for you, here in Hungary we have a lot of thermal baths. For example, in Hegykő is about 20 minutes from Sopron. Then Lutzmannsburg, it is also in Austria. It is about half an hour, and Bück, and here is Scharbach. They are about 1 hour from here. The thermal water is not only for the adults, for the young people too, you can see. Yes, and that was mine.
Thank you very much. I think that you could gain some very interesting insights and information about Hungary. One thing that wasn't specifically stated, but I think that it's safe to say that we also like to boast about all of the nice accomplishments that we have. As I'm sure that every country likes to show them off, but yes, these are really some of the accomplishments that our country did and our countrymen did, and we're very proud of it, of course, naturally. We are actually running a little bit ahead of schedule, and I was thinking about how to go about this. I would like to thank you, both of you, for the nice presentation, of course. And attentively, we are supposed to have a little break today for the lab work that you will be doing. It will be organized a little differently from the previous workshop. The biggest reason for that is that we will be having non-destructive tests, and then we will be, as I said, in Poland when we were there, we will be breaking stuff, which will be exciting, but we will be breaking the same specimens that we previously examined with non-destructive testing. So this means that we will have to go in a certain order. So we will actually be starting the first team's cruise will be starting with non-destructive testing this afternoon. And then after that, tomorrow, each of the teams will go for non-destructive testing and have destructive testing as well. And also tomorrow's program will include, for each of the groups, we will be going to the visitor center of the university, which is called Lignum, which is a few steps away from here. So we will be also visiting that. About the distribution of the teams. Each of the students has a little handwritten letter on the on your name tag, which says either S or B or L, which stands for spruce, pine, piner, and large. And this will give you the information. All of you have the program in your little bag in there, so you will be able to see where you're supposed to be going. I will be showing you, of course, where you need to go at the beginning of your of each of your lab sessions. On Wednesday, we will be going for some company visits. We have agreements with IKEA, which is down in Stockholm here. They have a plant which they mostly have to do with furniture made out of laminated chipboard, particle board, different kinds of office furniture and other things like that. We will be visiting their company, their plant, and also we will be going to Village, Hungary, which they have. They are window manufacturer and they make roof windows for inclined roofs. So that's actually quite interesting. They have very advanced technology and they have some very interesting things, including even some of the treatment of the glass that they are doing there. So I think that will be also very interesting. And in the Wednesday afternoon, we were going downtown. We are planning to visit the museum. We have a museum of forestry, so we are planning to go make a visit there. And also the fire watch tower, which is kind of the symbol of Stockholm. We can go up there. They have a very nice view of the city. Unfortunately, I won't be able to give you a regular guided tour of the city because I don't have a permit for that. And in Stockholm, you need a permit if you want to guide a bigger group around town. So, but you can feel free to walk around and explore some of the area. Our downtown is a very nice historic downtown from the Middle Ages. We have beautiful buildings in there. We have a few museums, so I think this is worth a visit too. Thursday is devoted almost entirely for preparing your reports and your presentation for Friday. It has been, at least my experience, but I think we also discussed it with some of the other teachers, that this is usually the part of the workshop that you guys don't always seem to have enough time for that, so we will be doing that, except I will be giving you a short presentation in the morning that is intended to give you a few little hints and help about how to prepare the reports and the presentations. Maybe this will be helpful for that. And then Friday morning, of course, as usual, we are going to have a closing session, which will include all of the teams giving the presentation about the lab sessions and the results that you found, and an evaluation by teachers, and also the announcement for the final workshop, which will be in Finland again. Also, I think Mika, you have the sheets for the sign-up sheets for the for today. It's already started again. Okay, thank you very much. Okay. So, like I said, I've only 45 minutes for that. I think you will have a good idea of what to do. This will be our meeting room. We will be coming here to meet every day. Oh, yes, a few things that I also need to announce now because I don't know where we will have a chance to do that again. Tomorrow afternoon, we have an optional evening program. We have an interesting little artifact here in Stockholm. It's called Taroli Castle. It's also called the Crazy Man's Castle. Don't tell the guy that I said that. Because it's called the Crazy Man's Castle because it's not like from the Middle Ages or anything like that. It has been built by one guy. His name is Taroli, that's the name. And he built it from the ground up by himself, and then later just with his family he built everything, and he has a little unofficial collection of interesting artifacts there and things like that, and we will be going there, visiting there. It will be at 4 o'clock. I originally intended to make it at 5 o'clock, but I haven't realized that because of the daylight saving time, switching to the daylight saving time, it's getting dark a lot sooner, so we need to start at 4 o'clock immediately after the last team has finished up their lab session. We will be doing that, and I will probably not the meeting point. I haven't decided on the meeting point yet, but we will be doing that. So if you want to come along for that, I suggest that you do. It's kind of a nice. It's about half an hour, 45 minutes walk out there. It's up in the hills, not very far from here. Maybe I would say half an hour should be enough. I'm saying 45 minutes because it is my experience that if you have a large group, the larger the group, the slower it can go for some reason. But we will see. But I should say that we should be there half an hour. And also another very important point that I want to say, but I will tell you about this later on too, is that the field trip, we are starting for the field trip at 7:30 on Wednesday, and the meeting point for that will be at the main entrance of the university. Some of you, I think pretty much the Finnish people, you already know where the main entrance is, so this is where we will be meeting. And for the rest of you, by the way, I sent you a link, to all of you, a link about a Google map that I created about how to get around and find your way. I realized that for some reason the Finnish group didn't seem to look at that. Yes.
Main entrance is in the front of your
in front of the main building. So not where the dormitories are. That's our other entrance. But the other entrance is kind of that way from this. You should be able to see that on the map. Maybe I can come and pick you up at the dormitory maybe 5 minutes before that. Otherwise, we will be always meeting here and going from here.
Two together. Okay? Now I put the same rope. It's still bending, and as you can see, the length of the beams are a little bit different because of the curvature. So what we can do about it, we're going to eliminate the shear stresses inside the room, and we will see what's going to happen. Okay? So, all what I want to, instead of gluing it together, I just want to fix both ends of this little beam. And as you can see, the deflection a little bit elevated. Another issue is, if you do the same beam, but not flat-wise, but edge-wise, you can press very hardly without any deflection. And that's what we are talking about. Why is it happening? What is happening inside the beam? And what kind of forces, moments, stresses acting on the beam which prevent the different deformation, translation, or bending of the members. Okay? So let's start with this one. I don't know whether, can you see at the back? Too? That's fine. So as you can see, historically, wood is always used as a bending method. Old wooden houses somewhere in Scandinavia, say 2,000 years ago, without any chimney on the top board, are under heavy snow load, experience bending. The second picture is nothing else, just Julius Caesar's bridge over the Rhine, and you can see many of long wooden beams or members are exposed to bending. A modern light frame residential construction and futuristic would use somewhere in Spain, and we can see the wood is a very useful material. First of all, we have to discuss a little bit definitions. Okay, we are living in a three-dimensional space. Actually, it's four-dimensional because of the time, but let's do it first of all just in the three-dimensional space. And in a Cartesian coordinate system, x, y, z, we can locate any kind of point. The good news is that usually the beam analysis is made in plane, so we're going to degrade everything into a two-dimensional coordinate system, x and y, and we're going to discuss it a little bit later, okay? And what I really want to talking about is nothing else, just
the basic laws of Newton's, first of all, the first law. And the good thing is, the genius of Newton was that stated the object in motion stays in motion. Because it's very hard to imagine that this little marble roll on a perfectly horizontal surface without any friction will move forever after you give it a little push. It was really very well demonstrated in the space when a physics teacher just draw the tennis ball, okay, and release the string, and the object is moved totally horizontally in a weightless space. Otherwise, on the ground, because of the gravitational forces, it will drop. Okay, so it's a very important law, and all of the mechanical things apply. The next definition is Newton's third law, which says when there is an action, there is always a reaction which is opposite and equal in magnitude. Okay, first. Now, after that, we're going to discuss a little the state of balance between forces acting in the project. This is equilibrium. Equilibrium says that the summation of the forces in different coordinate systems, the force component x, y, z in a 3D coordination system should be equal to 0, and the moment effect, the rotational effect, should be equal to 0 as well. So keep it in your mind when we're going to analyze these. Okay. The next step, we have to discuss what is moment. Is the measure of tendency to rotate a body. We can mark it by this rounded arrow around the fulcrum point A, which is exactly equal to F times D around the same point, or equals with this force couple acting in the opposite direction. It's again a very important statement concerning the beam analysis. Well, have you ever heard about how we're going to convert forces acting on a rigid body, normal forces? Normal means perpendicular to a certain surface, convert into stresses. Nothing else, it's a very simple equation called normal stress equation, which says that sigma tension and the compression stresses equals to P over A. P sometimes denotes force, and sometimes F is denotes force. There is a big mess in the literature, so you can find different notations. I would like to ask you, just not like me, be consistent and know what you are talking about. Okay. It doesn't matter what you are using to mark a certain physical entity, okay, but you have to be consistent and you have to be know what you are talking about, okay? As you can see, I'm using P and F as a force, but forgive me, it's on purpose. The other thing is, what we have to discuss is the Hooke's law. Hooke's law states that the stress inside a certain specimen exposed to normal stresses is equal to the so-called strain, relative deformation of the body, multiplied by a constant, which is called the Young's modulus of elasticity, modulus sometimes very shortly said. And if we're going to pull this rod, which is fixed to somewhere, there is a certain kind of elongation. Here you can see the reaction force, action force. It's called a delta L elongation. Okay. And this delta L elongation can be expressed as strain divided by the total length of the specimens. And collecting stress and strain data, the slope of this linear portion of the curve is the modulus of elasticity according to this equation. We just have to rearrange it a little bit. And is valid for compression and tension as well. So far, everybody is with me? Good. I'm a little bit anxious because I've done it since 6-7 years ago last time, but it's okay. Look at the next slide. First of all, we are good scientists, okay, or at least we're going to be a good scientist, okay? Therefore, you have to keep it in your mind that this modulus of elasticity, what we have just described, is totally different for the three anatomical directions. So wood is said to be an orthotropic and inhomogeneous material, which is not really orthotropic, but we pretend it is, because of this little curvature of the annual rays. But sometimes, in another section of the wood, it might be very close to orthotropic. Okay. For the time being, I just want to mention, these are the modulus of rigidity, shear moduli, and the 6 Poisson ratios. So of wood, elastic properties can be described by these 12 entities. This is a certain kind of measurements what we have to experimentally determine in order to deal with the orthotropic nature of the wood. But don't worry for the time being because of the orthotropy of wood. Next step. What we have to discuss is the shear. What is shear? Shear force, top of shear force, try to slide two surfaces on the top of each other. As you can see, here is the glued specimen, and we try to push them. The bottom in that direction, the opposite in that direction, and this surface CDDA is sheared. It's usually a glue line in a glued specimen, but sometimes it can be for wood, the LT plane or the RL plane, and so on. How we can calculate the stresses occurring in this region? Here, first of all, the notation of this shear stress is nothing else just the Greek letter tau, and we use F and divide it by the area. So sometimes shear forces are noted again with a capital letter of V. So you have to use V over A in order to determine the stress. I told you there is a big mess in notations, okay, not to mention the measuring systems. Finally, everybody has to use the SI system, but it's not really enforced in every part of the world, anyway, especially in the United States. Okay, now, as you can see, we have a small cube here, a differential cube, and due to this shear force action, there is a certain kind of deformation. The y direction is not going to change, but there is an angular distortion which causes a delta x deformation of the curve. Now, the Hooke's law for shear can be stated by this equation, which is nothing as g times gamma, where gamma is angular distortion expressed by radians. Why? Because the tangent of the small angle is equals to the angles expressed by radians. And g is the modulus of rigidity or shear modulus measured by Pascal and Pascal. Keep it in your mind that taking this tiny cube, we discussed a little bit the equilibrium, okay? So they have a shear force acting in that direction or that direction. So you have to compensate the rotation effect, because this block is in equilibrium. Every tiny bit of this experiences shear stresses dually. Otherwise it will rotate. Can you understand that? That this rotation acts in that direction and that force couple try to rotate this one. That's why we can maintain equilibrium. Is it okay? So that's called the duality of shear stresses. Okay? So that was the basic. So we're gonna go to beam analysis. Well, beams, what's the purpose of the beam analysis? First of all, we have to identify the external and internal forces acting on the beam, and we're gonna collect it in a normal way. Okay, some kind of useful way we try to collect it. And how are we gonna do it? First of all, we have to create a simplified mechanical model. I might say, this is the real life situation. We're not going to do a very precise drawing of it, just we're going to simplify it. First of all, we assume this is a simply supported beam in order to maintain support conditions. We have a fixed pin connection here and a moving pin connection here. Actually, we don't have that one or that one. Maybe we have a half rigid pin connections here and there. But it's good enough for the precision of our computations. Okay? Secondly, we have to identify the external forces. What are the external forces? First of all, the load. Well, forget about, for the time being, the self-weight of the beam, okay? Now, we have a T force acting on the beam, okay? I use T again. Well, I was stealing this picture from an American book, okay? Now, we have to identify the reaction forces according to Newton's law. If there is an action, there must be an opposite and equal magnitude reaction. Okay? And here, you can identify some kind of reaction forces. What are the computations? First of all, if this is P, and this is acting on the center, okay, all the P's must be half of it in order to counteract. Is there any external force acting on the beam? External force. Okay. Excuse me? That's my P. That's my reaction force here and there. Are there any external force on it? Can you see any kind of arrow? No, there is no, except the self-weight of the beam, but we have already discussed it, that we're going to neglect that. Okay? No, so there's the situation. If it's dislocated somewhere else, how we can compute the reaction forces, the negative? Obviously, it's going to be a little bit higher here and a smaller there. We have to write two equations. We have two unknowns, one known force, okay? We're going to write summation of P's equal to 0. Since it's negative, this is positive, it's okay, but we have to write a moment equation, but I'm not going to get into this one. So we have to summate the moments along the length of the beam and equate to 0, and we can express one of the angles. Okay. We write the we locate the fulcrum here and start summing the moments. P times L over 2 and RB minus RB sub L. And we can express the unknown RB, and substituting into the first expression, the summation of P's equals to 0, we can calculate the unknown reaction force R. Okay? Here comes trouble. Are there any external forces? Naturally, because everything is in equilibrium. And we stated if the entire beam is in equilibrium, not moving, not rotating, not dislocating, and so on, we have to have every point of the beam be in equilibrium. So just have a section here, C, imaginary. So we try to remove this one. And as you can see, you have an external force here, and after that nothing. So there must be a V shear force acting in the opposite direction, okay? And since we have a force stopper which tries to rotate this little section of the beam, we need to have an internal moment which is counteracting that one. Is it okay? Are you with me? Similarly, in the other side, we have one external force here, twice as much external force here, so V must be in opposite direction, okay? And since this tries to rotate in that direction, this force couple, this section of the beam, we have to have an M prime, another moment, which will counteract it. Now, how are we going to locate this? First of all, every section of the beam will experience from L over 2 to A positive shear force all along the halfway of the beam, and here the shear will change the sign, okay, and there will be a negative because it's going upward. Does it make sense? So this is our shear diagram. So we are perfectly know along the length of the span what kind of shear forces acting internally in the beam. Okay? The second is the moment. How are we going to calculate the moment around this point here at C? Well, let's have a fulcrum here, and we have a moment by RA, and according to the definition of the moments, RA times X should be equal to this moment which is counteracting to a certain point, is equals to the moment at that point inside the beam. Is it true? Half times P times L over 2, that's the maximum moment. And here, if this, call this distance D, this area is equal to that moment. Strength of the strength of the material. And how are we going to do it? As you can see, this blue shear force acting in that direction, okay, and we're going to convert it into stresses, and this is just this is an excellent picture of that one, and as you can see, the shear stresses here and the neutral plane are the figures, and we have a formula to calculate this, 3b over 2a. And here, at the bottom of the beam, the shear stresses are 0. If we're going to convert this moment, which was the opposite of that one, right now I ordered the regular laws, okay, into stresses, and quite easy to do with a formula that I'm going to show later. Just keep it in your mind that this is the center line in a rectangular cross section, which is called the neutral axis or neutral plane, where the moments are 0, and at the outer fibers, stresses are maximum. Now, we are able to see, no, we didn't left, a stress state of a little beam and any locations. As you can see, at the neutral plane, it's a tiny differential cube, experiences only shear forces, the maximum shear forces, shear stresses, sorry. But here, which are compressed and some kind of shear stresses as well. If I want to mark here in the bottom side of the location, under the neutral plane, this arrow will point outward, okay, because it's tension. Anywhere based on moment and shear stress calculations, we can come up with the proper stress strip inside the beam. Why we are doing this? First of all, we have to get information about the strength and velocity properties of the beam. What is strength? Strength is a certain stress value at the moment of failure. So it can be compression failure, the maximum stress what a material can bear. It can be tension stress, torsion, or whatever. And what are the elastic properties? What we can compute from the beam analysis is modulus of elasticity and bending of accurately the apparent modulus of elasticity, and we can calculate the shear modulus. What we can measure directly? First of all, we can measure the specimen dimensions. It's quite easy. We can measure the magnitude of applied load. No problem. And we can measure the deformation. And what we can compute from these measurements? Bending stress, sometimes called modulus of rupture because it's an apparent bending stress. It's not pure bending, it's shear bias too. Therefore, that we call it apparent modulus of rupture. This is a little bit confusing, the modulus of elasticity. It's not a modulus actually, it's strength. We can calculate the apparent modulus of elasticity and the modulus of rigidity, shear modulus of harm. First of all, here is our actual testing setup. This is a load cell connected to a computer. This is a strain gauge, deflection measurement connected to again a computer. Okay. This is the schematic illustration. Actually, it's not the length of the beam, it's the span of the beam. Very frequently, they are mixing up the length and the span of the beam. The span is between the subfolds. The length, it can be anything. And we have a dial gauge, what we can collect with what we collect deflection data. So this is the actual setup schematic. During the testing, we're going to collect load, deflection, data first. All these can be collected, can be converted into stresses or strain, but for the time being, it's not. As you can see in the beginning, it's a little bit adjusted because it's not so nice, but usually it's just a simplification of the diagram. This is a straight line where there is a certain point when it's not straight line anymore, but it's a curved line. And what's going to happen here is called the proportional limit. Within this area, Hooke's law applies. And after that, cease to exist. Hooke's law ceases to exist. Different situations are happening. But I'm not going to get into this. No. First of all, how are we going to convert moments? First of all, how are we going to compute moments at the critical points center point on the limit. At proportional limit, we measure the force at proportional limit multiplied by the span of the beam and divided by 4, and we got the moment in Newton meters. And since we want to calculate the maximum stress, we need the maximum moment at the same location, called x equals L over 2, Fx multiplied by L divided by 4. It's two different values. Okay. This is over the proportional limit, this is below or right on the proportional limit. Okay. The second, now we're going to calculate the shear stresses along the length of the beam. As we could see in the beam diagrams, plus minus P max equals 3 times V over 2V, where the V is the shear force, internal shear force experienced by the beam, and this is the cross-sectional area of the beam. And if we're going to convert it into F forces, 3 times F for V. The normal stresses at the center of the beam at proportional limit or below proportional limit. What we measure, moment, or calculated by this equation, multiplied by C, divided by I. Similarly, which is over the proportional limit, maximum moment C times I, this is equals to modulus per object. The question is, what are C and I? Those are geometric properties of the beam. We have a rectangular cross section of the beam here. And as you can see, if I try to bend this beam by hand, it's quite strong. Okay. But it's not very strong. Why is it? It's the same size, same material. What's happening? Why I'm able to break it up in this direction, and why I cannot do it in the opposite direction? No. No. It's simply geometry. It's simply geometry. It's resistance of the cross section against bending. Okay? Let's suppose this is our cross section. I was able to draw it in that direction, but I wasn't able to draw it in that direction. It's nothing else, nothing to do with the material, whether it's steel, concrete, or whatever. This is the so-called cross-section resistance against bending. Very simply a problem. As you can see, C is denoted here from the neutral plane, z-axis, z-axis, okay, h over 2. This is called the outer fiber distance. Here the outer fiber distance, if I'm using it, this one, it's only 1 millimeter. Here, what is the outer fiber distance? At least 1 centimeter. Am I correct? Okay. This is called the area moment of inertia. This is the resistance of the cross section against bending. As you can see, I is bigger, cubically proportional with h, the height of the beam, and only linearly proportional to the beam. Is it clear so far? So I is very huge in that situation and small in that situation, flat-line situation. Now, if we want di I over C is sometimes called the section modulus for rectangular cross sections, and still you can see that A is quadratically proportional to the section modulus, and B is still linearly proportional. That's why the resistance of this cross section edgewise is much bigger than the resistance flatwise. Nothing to do with the material properties, nothing to do with the structure inside the material. It's purely geometrical structures. Here is the situation under the load. We can measure the deflection, okay, at force in the middle of the stone. This is the neutral axis, and we have already discussed it here. The shear forces are maximum, shear stresses are the maximum, and the moments are zero. And here you can see these computations. So this max deflection can be computed from the force times L to the third, 48 times E times operand divided by R. What are the unknowns? What is the unknown actually? The single unknown field. E apparent, am I correct? Because we could measure this one, we could measure this one, the span of the wave, we can measure the deflection, okay, this is a constant, that's the only thing. Because I is given by the cross-sectional properties. So, all what we have to do, express E from here, and voila, we are come up with the apparent modulus of elasticity of the wave. So, we define one elastic properties of the wood specimen.
Those are speaking very well. Some others who are not speaking English, and some others among me who are speaking some English but with strong Hungarian dialect. So I hope you will be able to understand me. It's okay for you? So if it is a problem, please stop me. I wanted to give you some brief information about the work what we are doing here in Sopron at the Joe Bodig Wood and DT Laboratory. What is few words about Joe Bodig? He was a student of a university before the revolution, 1956. He was not completed the university, moved to US, moved to Canada, and got a diploma at UBC and became a famous professor at Colorado State University. He was working on non-destructive testing of and when we started our MBT work here, we got a lot of support from Joe Bodig. That's why the name of the laboratory now is called Joe Bodig, and recently the head of the laboratory is László Bejó. Recently I'm working in the Department of Physics and Electronics because my originally background is physicist. I learned the only one Hungarian nuclear power station. Now briefly about non-destructive testing of wood and trees. It's a very special field, but after a training at the nuclear power station, when I was responsible for the integrity of the reactor pressure reservoir, I tried to utilize that knowledge here in Sopron, where this university at that time focused only for trees and wood. and I realized that there is a small international community who are working on non-destructive testing. And this field is completely covered the whole production chain from ceilings, trees, logs, lumber, food structures. And I wanted to summarize all this information now. There are books. One of them is written by Wojciech Bukur. At the moment she is living in Australia, but originally she was born in Romania. Acoustics. You will see acoustic has a major role in non-destructive testing. Of course, there are other books like Non-Destructive Evaluation of Wood, written by Roy Pellerin and Bob Ross. And here are some copies, front page of the proceedings of Wood and DT symposiums. Every 2 years, there is an international Wood and DT symposium. The last one was just a few weeks ago in Rio. You see quite a nice environment, and more than 100 researchers gathered who are working on this field. So, I will continue acoustics. Why acoustics is interesting? The wood material is a very special and unique material. It's created by the nature, and every piece of wood is different. Like everybody here in this room is different. That's why we need to somehow characterize the properties, and modulus of elasticity is the parameter which is quite useful parameter. I show you a much more easier way for determination of modulus of elasticity, the dynamic way. When we multiply density with velocity on square, we got the same modulus of elasticity. Of course, not the same value. Always the dynamic modulus of elasticity with this term is higher. But before I go on, let me explain why, what is modulus of elasticity. When we are thinking about long terms, it is always difficult to pick up what it is. But if you think about that, we have material, any kind of material, steel, rubber, we have a cross-section area, we have a length of the specimen, and we apply some force. The length will increase. So what is the change in length when I apply some pulling force like this? It's difficult to see. Of course, higher the length, will be higher the change in length. Higher the cross-section, it reverse. Higher the force, it will be higher the change of the length. But there is one more parameter which depends on material. If it would be rubber, it would be like this. And modulus of elasticity is the parameter which says the material properties, which makes these relationships, these proportional relations turn to equation. Okay, so modulus of elasticity is easy to determine when we have density and velocity in the material. It is predictor of modulus of rupture, predictor of strength. Higher modulus of elasticity means higher strength, and also longer fibers. And also the velocity is linked with microfiber angle. Have you ever heard about what is microfiber angle? Not really? Well, this is the microstructure. Let me ask you, who heard about microfiber angle in wood? Okay, sorry. This is really the microstructure. When we go deep into the material, we will see the vessels and the vessel wall. And the wall has different layers like S1, S2, S3. The most dominant part is the S2. Yes, and what is the chemical which is made by this wall? This wall is composed lignin and cellulose. And the
lignin is almost a glue. Cellulose, it makes the material strong. Cellulose molecules are long ones, and the order in the cell wall is not random, but they are roughly 100 molecules together, which is called microfibers. And these microfibers are oriented not straight, I mean not in the fiber direction, but there is little angle, like a spiral stair. And this angle relative to the geometrical axis is called microfiber angle. This is important for our point of view when we are speaking about velocity in the material. Oh, yes, here it is. This line is indicating the microfibers, and this angle is relative to the axis of the structure is the microfiber angle. Sound is propagating along the microfibers. That's why higher the microfiber angle, the velocity will be less. The juvenile wood, which is located close to the pits, has completely different properties than the matured wood, but also the material properties. Density is not too much different, but the stiffness, the modulus of elasticity, is very different. The material in juvenile wood has low modulus of elasticity and has, of course, low quality, as you know very well. That's why we are thinking about two parameters which says the quality of the material. This feature is coming from a New Zealand patent. Explains that velocity of the sound in fiber direction, it is a very good indicator of the fiber length. Higher the velocity square, will be higher the fiber length. And for those companies who are using this material for making paper, it's a very important parameter. This is another game. When we wanted to produce high strength lumber, it is possible to select high velocity logs. When the velocity, the sound velocity in log is high, in that case the lumber modulus of elasticity will be higher as well. Of course, in a log, as you know, the material properties is changing, not uniform, but the trend is clear. Higher velocity in log will produce higher strength lumber. This is the same feature in practical point of view. In this research, they grouped the logs in three groups: low, medium, and high velocity logs. And this is the stiffness distribution. You see, with the high velocity logs, they were able to produce high modulus of elasticity lumber. So this is the basics of the lumber grading. How to measure velocity? Later today or tomorrow you will meet this equipment, which is a timer which is dedicated to measure stress rate time. We have two sensors, and it just simply measure the transit time between two sensors. The velocity equals distance divided by time. We can measure distance with a ruler, and this equipment tells us the transit time. The time resolution is 0.1 microseconds. This is another application in testing oak seedlings, very young oak, and why it is interesting. Foresters found that those companies who produced high-strength lumber made good profit. They decided, the foresters, to measure the velocity in standing trees, and they sold out high-velocity trees, high-velocity logs, for higher price, and that's why they were able to gain with this business. But they decided to increase the wood material
models of elasticity by selecting the trees in a very young age. Very simple. They measure the velocity in seedlings. High velocity seedlings will produce high velocity wood material later. But it's not so simple. They do not only one measurement but two. They do in a 6 months old, very young age. When the velocity high, it goes to the production. Its seedlings go to the forest. If not, they are waiting for another year. 1 year later, when the age of the seedling is 1.5 years, they measure the velocity again. If improvement was high, it's put into the production. If still low, they waste. In this way, they are able to increase the wood material strength about 5 to 10%, and this is not negligible, of course. So this is just a few words about the patent. The patent holder is the Heiser company in the US, and this patent says this story more detailed. So again, grading trees based on stiffness, we would need to measure density and velocity. By a timer, we are able to measure velocity. It's not a complicated issue. Density is not so easy, but the density variation is much less than velocity variation. That's why the very simple approach, higher velocity will show us higher modulus of elasticity is working in the practice. So this is another timer dedicated for forestry applications. The sensors are equipped with sliding hammer, and it provides us an easy operation. One test, one cycle measurement moving to the next tree is 40 seconds. So again, a higher velocity, higher modulus of elasticity, higher strength, longer fiber, and low microfiber ink. Blocks. How to grade blocks? This is a very simple way. This is an old image. Now we are using a mobile phone and a very simple application. We hit the end of the log, and the longitudinal vibration, the sounds going up and down in the log, and we measure only the frequency of the sound signal, and frequency multiplied by the length and multiplied by 2 is simple but the velocity in meter per second. So this is one example of this application. So it is really easy and quick. The technique is based on resonance measurements, so that's why it provides high reliability of the measurements. So, evaluation of historical wooden structures, how to predict the strength of an old beam. Whenever we have an old structure, we wanted to save it for long. And the wood material properties is changing by time, depends on where the material came from. And according to our regulations, after 50 or 70 years of a lifetime of a building, re-evaluation is necessary, structural evaluation. The strength predictor we are using is stress-free velocity, and instead of density, we are using screw withdrawal force. This is the method how we are using a very simple timer, 2 sensors. The sound is made by a hammer impact, and we have immediately the stress wave time. We measure the distance by a tape measure, and we have the velocity. Density is a little more complicated. This is a special screw where the thread is removed. So only part of the screw, 18 millimeter, is active. And when we simply withdraw the screw, we got a parameter which is proportional with density. Low density, low withdrawal force. Of course, it's a very local parameter. The user who is the user of this equipment needs to check a uniform area. I mean, far from knots, relatively far from cracks, and it will provide quite a good density parameter. So, when we are using these 2
strength predictor, velocity, and screw withdrawal force. This is the predicted strength. Predicted strength for this is coniferous, this group, and this is oak deciduous. We got quite a good relationship. Of course, not a straight line, it's not a measurement, it's just a prediction of the strength, but the accuracy of the strength prediction is plus minus 10 megapascal. It's not too bad. Okay, let's move to lumber grading. Again, according to Eurocode 338, the strength class depends on density and depends on modulus of elasticity of the material. So that's why modulus of elasticity is so important. And again, the dynamic is determined by density multiplied by velocity. This is an easy way. We have a hammer, the lumber, microphone, and FFT analyzer. You will get a chance to use this simple FFT analyzer, which is based on PC, sound card, and microphone. Every house we have at least one. And when we are using this software, pick up the vibration, and this is time, and this is amplitude. And this is still amplitude, the vertical axis, but the horizontal one, instead of time, is turned to frequency. This will give us the vibration frequency. So, frequency multiplied by length and 2, we got the velocity. It's quite easy and quick. Different type of lumber grading machines are working in this principle. This is widely accepted in Scandinavia, and nowadays this technology is moving south. So also available here in Sopron. Practical realization, computer. In this case, we are able to measure density. When we know the dimensions, we measure the weight, we have the exact average density. And this microphone picks up the sound, and this small hammer is used to generate the sound. In this process, one test takes 1 second. So it's really fast, easy to install in industrial condition. This one is another realization. In here we have two balances, the two supports, industrial balance, and here we have a laser which measures the length. Unfortunately, in Hungary, the sawmills producing lumber length is not so accurate. So that's why if we want to measure the modulus of elasticity, we need to measure the length. So this is still fast, and also this equipment is past the initial type testing according to Euronorm. The number is given here. It's quite accurate test. We already tested almost 2,000 full-size lumber. The S-line grade, this is what we measured by this grading machine. And the optimum grade is determined by testing machine. This is a large-scale testing machine. And what we got, we compared the two grades. Here you see the C grade is coniferous. Higher the number, higher is the modulus of elasticity. And in the best case, all the numbers are in this axis, but sometimes we upgraded the specimen, upgraded the number, sometimes downgraded. Downgrade is not so serious, but upgrading is could be provide serious consequences. But there is strict regulation, which is the low amount of upgraded level. So this testing machine was fulfilled the EU requirements. This technology is applicable for large scale as well. Here we have a glue lamp. We are able to use the same technology, and we have the models of elasticity of the whole glue lamp. Recently, this is my favorite
Topic, tree stability. This is linked to urban area, and we like trees, but in case of storms, the trees are a source of danger. Using the stress age timer, what we earlier used to predict the strength of the wood material, we are able to detect internal defects like cavity or decay in trees. When we have two sensors, just we measure how long the sounds penetrate through the material. Whenever we have some problem in between the two sensors, the arrival time is higher, of course, because the sounds need to use a longer path. In practice, it is so simple. Two sensors, timer, hammer, and you need a distance. That's why we are using caliper. Evaluation. We know what is the impact velocity in the material, and we have a measured velocity, and we compare the reference velocity to the measured one. When this deviation is higher, the defect is higher inside the material. It is working really well. Well, it's moving. I'm sorry, it is not moving. What is in here? Here we have a disc, an oak disc. We did a stress wave velocity test. It is just an indication that sounds never propagate along a path. It's a three-dimensional phenomenon. It's a two-dimensional representation how the sound is propagating. This line, it is indicating the wave front. The wave front every 20 microseconds. So the velocity is quite high. Velocity perpendicular to grain is around 2,000 meters per second. In fiber direction, around 5,000 meters per second. So that's why we need to use quite accurate time measurement. So whenever we artificially make a defect like this, the sound propagation will be different because sounds cannot propagate through. That's why the arrival time will be longer. This is, I'm sorry, I don't know why it is not moving in here. So, when we apply more test in a plane, in these more sensors, we have 6 sensors. We are able to build up two-dimensional images of the velocity. Here we have 15 lines. Most of the lines, velocity was above or around 1,000 meters per second, but those lines which went through this hollow, it's dropped very much, 400, 600 meters per second. In this way, we are able to identify the location of the defect. And this is the practical realization. Sensors on tree, and the computer collects the time data. Of course, we are able to test not only trees, not only discs, but rectangular structures as well. In practice, it is successfully applied for watching tower evaluation where the cross-section of the beam is found. Just few images. This is a playground of a nursery, and this tree from outside looks perfect, but when they did the test, it was perfect at ground level, but found big cavity, 1 meter and 1.7 meter high. So they decided to cut because in the daytime this area is full of children. What they found after felling the tree is the almost intact part of the ground and very big hollow, the levels where they did the test. So we believe that they removed the tree in time before it was made some problem. So this is just the software that we are using for this type of acoustic tomography investigation. This is the geometry in case of irregular geometry. This is in case of 12 sensors. This is the measured time. When we hit one sensor, this is 0, and all the other data is the transit time in microseconds. And computer built up a time matrix, Here we have almost 100 different lines, so the reconstruction of the cross-section like this is possible. In this particular tree there was some decay at the small part. It's a big tree with big cone, but we decided to keep for longer. For this reason we calculated safety factor. What we did, we calculate the stress made by the wind and compared with the strength of the material. To simplify the case, the blue area was intact and this area was the part of the tree which was not holding the structure, because we are thinking about the trees as load-bearing wooden structure. Of course, we need the load of wind, to calculate the wind load, we need the cone surface area and other parameters.
All of them. These are the treated ones and all of them. Yeah. These the other ones. Yeah, start here. It's an ultrasound system. You previously saw this the presentation of Dr. Divosh. Yeah. Guys, I would like to introduce this for everybody, and we will start in each part. It's a normal ultrasound here, like in the doctoral, like checking the baby and the mom. You have to put this contact liquid to the sensors, and this provides better connection for the sound. First of all, everybody have to check the correction time, and also the mass of the samples, and at the end, despite this type of measurement, you can calculate by your own. The other type of measurement we will calculate with the computer, because those equations are a bit complicated. Thank you. Okay, this is first, and the other one is I made this kind of paper now. We will use this sponges for under the samples, and these beers with the rubber one, with the steel one, and with the wood one. Yeah, but maybe the steel one don't. You can try. Okay, this is the program, FFT analyzer, and first you have to sign the places of the sponges according to the paper. It's 0.22 of the length of the sample at the first measurement. At this I measure, and the sponges have to be there. And also I signed the place of the microphone. Sorry. This whole button is for keep the result there, because for every sound it's changing. Okay. H. Yeah. At the first measurement, you have to check, you have to see the first peak, the biggest one. It's now 901.1 hertz. And so on. And so I will have, it's the same as the other computer. But maybe you can start here with the treated one and there with the normal one.